All right, so we're going to talk about a condition called hyperkalemia. Hyper means a lot, right, or increase amounts of. The K, in this case, I like to think is for potassium. And emia means blood. So you have an increased potassium level in the blood. If you notice, before I continue, I do not want you to get this confused with HyperKalemia, because that means you have an increased amount of calcium in the blood. We're talking about kalemia, which is potassium. Let's think about this clinical correlate. Let's say, for example, you have a lot of potassium in your blood. Someone gives you an intravenous injection of potassium for medical reasons. Maybe you're dehydrated because you were sweating too much. And you got an overabundance of potassium in your bloodstream, which could be quite fatal if not treated. Let's say someone gives you way too much potassium in the bloodstream. What do you think will happen? Will we have an increased potential to trigger an action potential? I'm sorry, let me rephrase that. Will we have an increased probability of initiating an action potential or a decreased probability of initiating an action potential, and why? Right? And one thing I didn't mention to you before is, let's clean this up a little bit. I'm just going to clean this up right over here. I'm just going to redraw this so it's a lot less busy. Okay. Let's say there's potassium over here. All right. And the cell is at negative 70 millivolts. And there happens to be these potassium leak channels. Let me use a different color for potassium. Let's go with orange. Right? There happens to be these potassium channels. They're just very leaky. You don't need a neurotransmitter to bind onto them. What happens is this is kind of leaky. So naturally, potassium will leak out, and that contributes to the negative 70 millivolts right over here. Right? Let's say we accidentally give our patient too much potassium. So I'm going to draw a huge potassium icon right over here. Will potassium be more or less likely to leak out of this cell? And the answer is, what did you say? Right, so the potassium would be much less likely to leak out of the cell now, because there's so much potassium on the outside of the cell. Right, so the cell now, instead of being our negative 70 millivolts, it's going to be less negative. It's actually going to be maybe negative 60 or even negative 55 millivolts, because this potassium here won't want to leak out as much. So we're actually going to have an increased probability of an action potential. So if you were to increase your extracellular concentration of potassium, that's gonna decrease the leakage right over here of potassium out of the cell, and cell is closer to threshold, which means the cell is hypopolarized or depolarized. Now, I don't like to use the word depolarized that much, because usually some students hear the term depolarized and they think it's the initiation of the action potential, and it is, right? So I like to just call this hypopolarized. The cell becomes a little less negative. It gets closer to threshold. Because the intracellular potassium doesn't want to leak out of the cell anymore. So now we have more potassium inside of the cell. So the cell, instead of being our negative 70 millivolts, it's going to be closer to threshold. So you have a higher probability of action potentials. And you're probably thinking, well, isn't that a good thing? Don't I want more muscle contraction? Don't I want more nerve signals? And the answer is it depends, because you don't want to trigger an action potential that is very persistent over time. Otherwise, you can fatigue certain parts of your body.